So to continue from last hour, as we see that raindrops and snowflakes provide a useful signal return. And it was not long after the successful development of radar that radar was being used to detect rainfall, detect precipitations in our atmosphere by meteorologists. Shortly after the Second World War, meteorologists came up with equations how to describe their rainfall. They came out with so a raindrop, for a typical rain, this diameter of a raindrop is in the range of 1 millimeter sphere. It's almost spherical for such small raindrops. And the rainfall is usually described as a rainfall rate in units of millimeters of rain per hour of time. This is rainfall rate. And Marshall and Palmer, two meteorologists, found in 1948, found an experimental relationship how to get the number and size of raindrops from the rainfall rate. And their experimental equation sounds like this. So Z is now the reflection, and Z is 1 millimeter spheres to the power of 6. This is what we need in our equation here. This is 6 power per cubic meter of volume. This Z, well, they defined this Z, it's a little bit strange numbers. This is meters to cube power, but it's still millimeters to the 6th power. This is actually, this is equal to 10 to the minus 18th power of meters cube. Just to see that these units are a little bit strange, but they're made practical, this unit for a practical rainfall. Of course, we do not have water just pouring out of the sky. We have raindrops that are much smaller, mostly it's... this is now equal to approximately, according to Marshall Palmer, 200 times this rainfall rate in units of millimeter per hour to the power of 1.6. So we have this connection in between here. This is our unit. And our Z0, this Z is frequently given on weather radar maps, as you can download on the internet. You can look out for Arso in Slovenia or somewhere else. Z is usually defined in decibels. dBz is the unit. And this is 10 times logarithm of the actual Z in linear unit divided by this reference. Z is 1 millimeter to the 6th power divided by meters to the 3rd power. This is also called Z0. These are all practical units for practical rainfall measurements. What are now the practical values of this Z? So if we have, if I write here Z, we write here the weather effect. If we have Z at 20 dBz, we have very light rain. Maybe just a few drops. If we have 40 dBz, we have normal rain. If we have 60 dBz, we have hail. We have hail. So hail is the strongest precipitation. It contains large ice crystals. Things in hail, the ice crystals in hail are much larger than 1 millimeter. That means a very strong radar reflection. And now from these figures, you see what kind of radar do we need here. What kind of radar do we need? So we need a radar with a suitable wavelength. The wavelength is not the same. The wavelength, the radar cross sections is very much dependent on the wavelength. And what we are using, what things started, what is still being used on the aircraft. On aircraft in their nose, you know, passenger aircraft have a round nose usually. Black, that's a radome for a radar, work at a wavelength of around 3 centimeters. Ground-based weather radar. Weather radar works at a wavelength of 5 centimeters. Please note here that what happens if we go to shorter wavelength, what happens if we go to longer wavelengths. If we go to longer wavelengths, we cannot measure any reflection. Because this thing simply, if the wavelength is growing, we have no reflection back from raindrops. If we go to shorter wavelengths, we get all the reflections already at the beginning of the rainfall. We cannot see inside the rainfall because all the radiation is already reflected by the first raindrops in this rainfall. So that's the reason why of these choices. In fact, the choice of 3 centimeters for aircraft is a historical one. Such radar were installed on aircraft already in the Second World War for navigation, for bombing, aiming, military purposes. And they were also used for weather. Nowadays, pilots are trained to use a 3 centimeter radar, and that's the usual radar they have on their aircraft. The radar would work better actually at 5 centimeters, but pilots have been trained to use the 3 centimeter radar. And of course, on a passenger aircraft, you do not need a very long range radar. It's enough that you watch 10 kilometers or 20 kilometers in front of an aircraft, and to avoid hail. Hail will damage any aircraft. Ground-based weather radar, like the one used by the meteorological agencies, the one you can see on the web, those use 5 centimeters in order that they can reach 100 kilometers or 200 kilometers in free space to the weather formations they are observing. That's the reason why. So how do we now calculate our radar? We have a radar equipment that has a transmitter and a receiver. We have an antenna. The antenna has a beam here, a beam of radiation. For my derivation now on the board, I will use the assumption that this beam is simply conical. It's simply conical beam that has an opening solid angle omega here. So omega is simply 4 pi divided by the directivity of this antenna. The antenna has a directivity d. If I have a more complex pattern, the calculation becomes more difficult. So now this beam gets through a region of rainfall. So here I have a cloud. And from this cloud I have a rainfall. In this rainfall, choosing a suitable pulse length on the radar. So if my transmitter here is transmitting a pulse of, not delta, too many letters. I get too many letters if I use delta here. So T pulse is, say, 3 microseconds. This is not far from real. What do I observe here? I observe a certain volume of precipitations. I observe a certain volume, where this volume has a cross-section A, and this cross-section A is simply the distance r here to the cross-section, r. A is simply r squared times omega. That's the cross-section. And what is the distance here? The distance depends on my pulse. So this distance here, L, is equal to time of the pulse multiplied by the speed of light divided by 2. Why divided by 2? Because if I want this reflections to sum, when the pulse is over, when the pulse has finished, I get a reflection here. The first reflection I will get to sum from the pulse has a rectangular shape. So I get the final reflection of these droplets here, and I have the first reflection of this area here, and they need TP half to come up here and TP half to return back. So that made the whole timing of the pulse. That's the reason why we have 1/2 here, because it's one way here and the other way around, so that they will sum up together. So this is now our calculation for this volume here. So the volume, I have here the volume I am observing. Volume is A times L is now r squared omega, here multiplied by TP C0 half. That's the volume that's working. Now, how do we get the cross-section of radar cross-section of these drops in the volume? So the radar cross-section, we have here reflections from many water drops, not just one. There are millions of water drops in this cross-section. These reflections from single cross-sections are not synchronized. If they are not synchronized, it means that I have a sum of phasors, and all these phasors have a random phase. A random phase between them. So the cross-section, I simply sum the power. So the reflected power is simply now the sum of each individual droplet. Or the overall radar cross-section will now be simply the sum of individual cross-sections. Individual cross-sections of the simple water droplet. So cross-sections here simply sum up because cross-sections are directly related to powers. And the phase is random, so if the phase is random, only the power sum ups. This reflection is really diffused in all directions. Now, how does these things look like? What is the reflection coefficient of a single droplet? The reflection coefficient of a single droplet, sigma I, is now sigma I over n drops. Number n is the number of drops here we have. Sigma I is now the equation I had over there. So is p to the 5th power, lambda to the 4th power, diameter of the drop to the 6th power. And how many drops do I have there? How many drops? What is n now? What is n now? Now is this is number of raindrops already containing 2a to the 6 over cubic meter times the volume. So this thing here now, which will be pi to the 5th power, lambda to the 4th. I already have this contained in z, z times the volume. Z in linear units here, times the volume, and I have the volume of the active area I'm actually observing with my radar written here. Z times volume as well, Z already provides this 6th power of diameter of drops, and I need not care now about the diameter of real drops. The real diameter of drops is already included in Z. Of course, when the rainfall rate increases, also Z increases, but inside Z also the diameter of single drops increases. But this is actually not important for me because I am given Z. Z is given, so I'm not interested what the raindrops are. I'm only interested what their average radar cross-section is here. Here's the 4th power. Just want to rewrite it better because it was not nicely written. Lambda to the 4th power. So I have now everything ready for my calculation. So I have a certain transmit power here. This power is now, I want to see what is the actual, with what S0, I'm actually illuminating my S0, I'm illuminating my volume. What is now S0? I will write without the vector sign, we know what this X0 is, what is coming from the transmitter. This is power of the transmitter divided by the area I have here. The area is actually here, r squared omega. This is now S0 coming to the area being analyzed. And omega is given, of course, by our antenna. Now, what is the reflected power? The reflected power is reflected in all directions. It goes all the way back to the receiver. So what is the S reflected? S reflected here, so S directed here. S reflected here. What's the S reflected? It's this power is being scattered in all directions. So it's 1 over 4 pi r squared. And the actual power is how much actual power do I have? Is S0 times the radar cross-section sigma. And what is the power in the receiver? The power I get in the receiver is S reflected, I get as a reflection, times the area of the antenna, and maybe the efficiency. I will forget the efficiency here. So, okay, I could write the efficiency, but prefer not to write the efficiency today. So let's say the antenna has an electrical efficiency of 1. I don't want to use the letter eta because I use it somewhere else in my textbook, and I don't want to mess up with the efficiency. So this area, effective area of the antenna, is now directivity of the antenna times lambda squared over 4p. Okay? So we have S reflected times directivity times lambda squared over 4p. Oh. Now I have to combine all these equations just into one equation. S reflected here is now C. Yes, I have to write all these quantities I have here inside this equation. So rewriting S0 4 pi r squared in the denominator. S0 is P of the power of the transmitter divided by r squared times omega. Okay? And sigma, sigma I have it here. Sigma I have it here. Here is sigma. Is pi to the 5th power over lambda to the 4th power times z in linear units times the volume. Volume is r squared times omega times t pulse c0 over 2. And let me see whether I have everything here. Yes, I still need, yes, this is S. And now I have to plug S in here, okay? Have to plug S in here, so this is now. My directivity was just to rewrite the directivity. I need here, directivity was 4 pi over omega, okay? So just to write the directivity here and the S here, the equation becomes quite long right now with all the quantities. Power of the transmitter. Maybe I could cancel out some of the quantities over here. So let me see, this cancels with this. And I still have many pi's over there. So 4 pi r squared. Pi to the 5th power, lambda to the 4th power, z, the reflectivity of my, the number of my raindrops, t pulse c0 over 2. And I still forgot, yes, I still have to put d inside, so this is 4 pi over omega. And I'm still missing now this S receiver. I have the lambda squared over 4 pi here. Oh. So now I have the complete equation written down for this radar. You see that omega plays a role only once. Maybe it was much better to actually write in place of this 4 pi over omega to write here d. It was much easier to work with if I write now here this directivity, or better to put in gain if I have some efficiency problems with that, then put in gain. Everything else cancels out. Everything else cancels out. We could put gain, but I prefer to have directivity over there. So now the whole equation is 4 pi is 16 is 32. So P in the receiver is power in the transmitter. I have here 32. Pi squared, pi to the 5th is pi to the 3rd power. Lambda. Oh, so I forgot here. Lambda squared, lambda squared. Directivity, T pulse, C0, directivity. And let me just check whether we got it right so we don't have made mistakes. I'm just checking with my papers that we didn't make mistakes over here. Yes, I think we got it right here. Just something I forgot here. I wrote this equation, but I should consider that my water drops have a dielectric factor. I forgot the dielectric factor here. Sorry for this. So here should be the dielectric factor, k squared. Also here, k squared. It does not change much the result. And where should I put it right now? So I should put it in sigma. I should have k squared here. It doesn't change much the result. K squared here. K squared. K squared. But this is 0.93 squared. It changes by 1 dB the result. That's not much really. And half a dB. K squared changes by half a dB the result, so it's not much. And now this is the final result we got for this weather radar. So let me just write a typical example what we have here. If we have, just write it down, a transmitter of 100 kilowatt, 100 kilowatt. That's not for peak power for a pulse of 3 microseconds. T pulse of 3 microseconds. This is not huge power. This means average power 100 watts. Usually the pulse to the duty cycle of this pulse is about 1,000. So this is about just 100 watts peak power. So it's not that large power. This L is 450 meters. Just to see what we're going. So the spatial resolution of this radar with 3 microsecond pulse will be 450 meters. Let me see just the antenna. Yes, the antenna was taken as this directivity or gain of 40 dBi. In this case, what we get here this power to be with all this data and lambda 5 centimeters. We're taking lambda 5 centimeters for a typical weather radar. This is going to be around minus 65 dBm for a z equal to 40 dB for a typical rain, dBz. At a distance, yes, I forgot to write here distance. R squared is missing here. R squared is missing. For a distance, R of 100 kilometers. A range, so at 100 kilometer range, typical rain, 40 dBz. This minus 65 dBm is quite a strong signal. For a radio, your Wi-Fi equipment will work fine with minus 65 dBm. So we get a pretty strong signal. What we should add here, the only thing we should add to this expression, that our real antenna does not have a perfect conical beam. So this was a conical beam. A perfect conical beam of the size omega. A real antenna, a real world antenna, has a shaped beam. So the beam is not a cone, the beam is an analog shaped beam. And this analog shaped beam, what does it do? It illuminates strongly the center of the rain rather than the edges. There is a slight decay. And usually this real antenna produces P receiver prime, about 1/2 of the P receiver we calculated here. This is true for a Gaussian beam. Gives a factor here of 1/2 because the beam is not uniform, does not provide uniform illumination all across. The illumination slowly decays. And also the reflection from the edges of such a shaped beam is weaker than the reception from the center of the beam. So, and altogether gives about 1/2. So this gives about minus 68 dBm. I hope I wrote everything, all the equations correctly. It's still a very strong signal, but just to be accurate, I wanted to add this factor down there. We have. Zamańka, Z is missing here. Z is also missing here. Z is missing here. Here we had Z, here it was missing. So Z is missing, everything else is correct. So usually you put here 64. If you approximate your beam to be Gaussian, this is not, it has no background, the beam is Gaussian, but it's a good approximation. It's a good approximation to take 1/2 of this value. It is not accurate. You get even more rude approximation in some papers written by meteorologists. If you look what meteorologists write about meteorological radar, then it's a real problem. So this is about our radar and about spherical raindrops. But the raindrops are not spherical. The raindrops do not have a spherical shape. What does that mean? And now I have first to describe you here an artist's conception about the raindrop, the teardrops. Artists usually write these things as this. And here they come out with teardrops, shaped like this one. A child crying and teardrops shaping out. So artists say that teardrops are this shape. Moving in this direction. This is actually not true. Artists have never seen a raindrop in their life. That's the problem. Real raindrops are this shape. Why do teardrops appear like that? Because we usually observe drops moving on a flat surface. And we have some surface friction on this, and that's the reason why the teardrop is elongated, because of friction here. But in real raindrop has air pressure here. So the real model for raindrops is not a prolate ellipsoid, like here, so an elongated ellipsoid, but rather a flattened ellipsoid, an oblate ellipsoid. That's a big difference. So raindrops have this shape, not these shapes. So this is artists' misconceptions about raindrops. Raindrops are not teardrops flowing on the surface of a solid surface. Raindrops or teardrops flying in air are flattened rather than elongated. That's a big difference. Where does this make a difference in our radar cross-section, all the calculations we had made? We have for horizontal polarization, okay, well, let's write EHP. And for vertical polarization, EVP. The radar cross-section for vertical polarization is always smaller than the radar cross-sections for horizontal polarization. The effect is larger for horizontal polarization because raindrops actually have a larger size in the horizontal plane rather than in the vertical plane, because raindrops are flattened. due to air pressure slowing their movement down there. You can actually see this with your own eyes with just another physical example. Certainly for your vacations you're going to the sea. Have you ever seen air bubbles in the water? Larger bubbles, larger air bubbles in the water also tend to be flattened since they meet water resistance in their movement to the surface. And large air bubbles always get flattened. They don't get elongated, they get flattened. And that's the reason why the effect for horizontal polarization is much larger than for vertical polarization. Of course, with raindrops, not with 1 millimeter. With 1 millimeter, the raindrops are perfect spheres. But as the raindrops increase with heavier rain and with hail, then the horizontal cross-section will be larger than the vertical cross-section. In fact, by measuring with our radar, changing the polarization here on the transmitting side of our radar, we can measure what is the actual size of our drops. Because the Marshall-Parmel equation only relates the rainfall rate to the factor z, the number of drops, of 1 millimeter drops per cubic meter. These are 1 millimeter, number of 1 millimeter, density of 1 millimeter drops in 1 cubic meter of volume. This is the factor z. And in fact, on many websites, when you look at the radar image on many websites, the scale is given in dBz. The only problem is ARSO, because ARSO does not know what dBz is, our local meteorological service. But everyone else refers this in dBz. So 0 dBz is almost no rain at all. 0 dBz is 20 dBz is half a millimeter of rainfall per hour. 60 dBz is 200 millimeters per. 200 millimeters is already a flood. Fortunately, hail do not last that long as 1 hour. Hail just lasts a few minutes, but it does lots of damage in 1 minute. There is yet another problem with, so we use now a whole 2 hours just to work out the weather radar. I hope I didn't forget something here. I forgot Z. The problem is our radio links. Our radio links going through precipitation. So I have 2 antennas for a fixed microwave radio link. And now I have a cloud here that has precipitation. Now, what are the effects here? We had additional attenuation. On this precipitation. But there's a difference in the frequencies involved. Say, for frequencies below 3 gigahertz, I have almost no effect. For a frequency around 3 gigahertz, I have just the dielectric loss in water. Water is not a good dielectric, it has some dielectric loss. I have both effects here now up to perhaps 30 gigahertz, where the only effect I can see here is Rayleigh scattering. And here I have both effects. Rayleigh scattering is, of course, a function of the raindrop size, while the dielectric loss of water is not a function on the water drop size. It's just a function on the quantity of water I have in cubic meter of volume. And beyond here I have only also Rayleigh. Well, up here I have almost no measurable effect. There are several tables to calculate, being from practical field measurement, how to do these things. And even the ITU has published already years ago many tables. How do this thing? I will try to show you one of these tables here on the computer. Just let me start up the computer. I hope I have the remote control here. Just to show you the order of magnitude of these effects. But it's better I show you a prepared drawing here. So let me see it here. Should be this one. Let's see. No. One up. Okay. So now we have what is the magnitude of this effect? Here we have the rainfall rate from 1 millimeter, 10 millimeter per hour, 100 millimeter per hour. We cover the normal range of rain. So this is just very light rain. This is very heavy rain. Not hail yet, but very heavy rain. This is the ITU recommendation R838/3. You have this type of tables published on the internet. You can find them out. They have been made from many different measurements, and they tried to assemble equations, put in the equations. This is the solutions of the coefficients given in the ITU tables. This is attenuation in decibels per kilometer. 0.01 decibel, 0.1 decibel, 1 decibel per kilometer. You see that at 3.5 gigahertz, you are hardly going to measure anything. 0.1 decibels. 0.1 decibels even for heavy rain here. While things are getting worse at higher frequencies. At 18 gigahertz, at 10 millimeters, so this is moderate rain, 10 millimeters per hour, moderate rain, you already have 1 decibel per kilometer. On a 50 kilometer link, this is if you have rain all along this link at 50 kilometers. We are going to talk more about the statistics of this next week. I'm going to talk more about statistics. You already have at 50 kilometers, you have 50 additional decibels. So here, 50 kilometer link at 18 gigahertz is not going to work. Things are getting even worse when you go to higher frequencies. When you go to higher frequencies, any amount of gain you have, you kill this communication. The loss you see goes up to, say, between 2 and 5 dB per kilometer. You cannot expect this link to cover distances more than just a few kilometers in the millimeter wave range. 30 gigahertz is 10 millimeter wave range. So in the millimeter wave range, these links will not go over longer distances while raining, at rainfall. So this is just to give you an idea. And you see the curves are written both for horizontal polarization and vertical polarization. The largest difference is at low frequencies. At low frequencies, the raindrop shape gives this difference. The higher frequencies, these raindrops are already so large compared to the wavelength that the shape of the raindrop has little effect. Both curves are similar. Of course, the horizontal polarization attenuation should be larger than the vertical polarization attenuation. Should be larger here. Why does this happen? Here the drawing shows for 18 gigahertz that at some frequencies the loss may be larger for vertical polarization than for horizontal polarization. This is just a limitation of the ITU equations and tables and coefficients. They could not prepare coefficients just for any possible communications. And of course, this has no physical explanation. Always the effect is larger for horizontal polarization. This is just the limitation of the tables and the way this, they tried to put this polarization, these equations into as few coefficients as they could. There are just 2 coefficients for every frequency to be plotted out. And this is just a limitation of the tables. This is physically not true. This does not make sense. What happens here? But this is just to show you the limitation of tables, because tables were made quite simple. Once upon a time, so in the 30, 50 years ago, people were much worried about rainfall attenuation. Today's things have changed. Today's networks are made flexible. If one leg does not work, there's always a way around to avoid that rainfall region, to avoid that hail region. Hail is very physically limited. Heavy rainfall is physically very limited, so you can always get the way around. If you have good routing in your network, then you can avoid these effects here. So this is not that much important today. Still at the highest and at the highest frequency, still rainfall is a problem. Where you have no alternate route, because here even distances are short at 80 gigahertz, 50 gigahertz, just a few kilometers links, and over a few kilometers, also a hail region has just a few kilometers across, so it's already there. We have the whole link inside this hail. You cannot find a way around this hail region. This is just about attenuation. I didn't want to talk much about attenuation because the radar stuff, I feel it's much more important. Especially for you going on to vacation, you will always look at the radar picture on the web. And that's the reason why the radar, I feel the radar is much more important than the link loss, because this link loss, you know, link loss may happen for many different reasons. Rainfall is not the only one. Ice may accumulate on the antennas. The thing that happened is different, but the effect is the same. You have attenuation if you have ice on the antennas. You have even more attenuation if the antenna has been stolen in between. So next hour we are going to look at the ionosphere. So changing subjects totally. I tried to explain, I used this year I used 2 hours just to explain the effects of precipitations. I never did this before. Or we went quickly through the explanation, or I tried to do, I want to have a detailed explanation of what happens in the rainfall area. What happens with the rain. That's the reason why I did this year. And next year we have next hour we have 1 hour for the ionosphere. I hope to be able to do the ionosphere in 1 hour, but even that is difficult.